Hello and welcome to the 9th lecture in my operating system development lecture series. Today I will be talking about a couple of peripheral interfaces that one can use in order to communicate with peripheral devices, as well as extension cards. First, I would like to talk about a very common interface called PS2. The interface has its name because of the fact that it was introduced with the IBM Personal System version 2. This system was, or rather this peripheral interface was used for a relatively long time, and therefore most of the viewers will probably remember using it. So, the ports looked basically something like this. It was a 7-pin port. And it came in a pair. I should probably highlight these a little bit more because they might not be visible. So this port is something called the PS2 primary port, which was standardized to be purple. And this is something called PS2 secondary port. And this one is standardized in green. So anyone that has used these know what they're basically for and what you usually plug into them. This PS2 primary port, it can be very safely assumed that what is connected to this is a keyboard. So there was a PS2 keyboard, and it had such a 7-pin ending that would go into this port, and this connector at the end, it would be purple in order to indicate that it should go into the purple port. So over here, you usually have the keyboard. As for the PS2 secondary port, which is green, most people will remember it as a mouse. But while this is actually correct, I would like to mention that there were many devices later introduced that used the PS2 secondary port, and they weren't necessarily mice. So different devices were made that used the PS2 secondary port, so you don't have a guarantee that it is a mouse. However, you can very safely still assume that it is a pointing device. It is some sort of pointing device. And again, this usually will be a mouse. Yes, so this was a widely used interface, and it had a couple deficiencies which later made USB keyboards and mice way more popular, and eventually this PS2 interface became less and less used. Now, one of such deficiencies was the fact that the PS2 ports did not have a functionality called hot plugging. So we sort of take it as a given nowadays that whenever you unplug something like your mouse, your USB mouse, and then you plug it again, plug and play mechanisms are run, and your OS configures everything, and you can just use the mouse again. However, this is actually a pretty difficult technological feat, and this is why for a very long time hot plugging was not available. An example of this would be the PS2 interface. Whenever you would unplug a keyboard and you would plug it again, it wouldn't function. You had to reboot the entire computer in order for this keyboard to work, and it had to be a hard reboot. This means that usually software rebooting wouldn't even work. So, these two ports, they have to be connected to something which is called a PS2 controller. This controller is responsible for managing this peripheral interface, which is PS2. The CPU can communicate with the PS2 controller using its I/O bus. So this PS2 controller has a data and command I/O port. It has those ports, and hexadecimal 64 is its command port, while 60 is its data port. Okay. So the PS2 controller, using these two ports, may be used in order to manage any devices that are plugged into the primary or secondary port, which will allow us to write drivers for a keyboard and a mouse. However, nowadays, as I said, most computers don't actually have PS2 ports, or even if the motherboard does have those ports, usually the user tends to use the Universal Serial Bus, or the USB. There's, however, a convenient feature of most modern motherboards, which is PS2 emulation. Oftentimes, whenever you have a USB device and the PS2 controller will be communicated with and such, an emulation will be performed in such a way that if you write a PS2 driver for the keyboard and the mouse, sometimes the mouse doesn't work that well, but the keyboard usually does. And your drivers for PS2 devices will work for USB devices as well. This is obviously something you shouldn't rely on because it's an emulation interface and it's not as widely supported, and writing native drivers is always better. But this is just something that I wanted to mention, that even if you write those drivers, they'll often work on real hardware with USB devices if a motherboard supports the necessary features. And laptops, they usually do that, since the keyboard is literally a part of the laptop. It usually, the laptop is configured well in order for the keyboard to provide PS2 input, and there's usually a touchpad which can work for the PS2, or it can emulate the PS2 pointing device pretty well. Okay. One other thing that the PS2 controller does is it maps the proper IRQ channels for these two PS2 ports. So the standard way that it does it is it comes to this port over here, the primary port. It gives it the IRQ channel of 1. So whenever a keyboard input is performed, it will trigger the first IRQ channel. If it comes to the secondary port, it will usually map it to IRQ number 12. And here is an important remark. If you want to write a mouse driver, a PS2 mouse driver, you always have to remember that the IRQ channel number 12, if a configuration of a programmable interrupt controller was done like the one that I specified in my previous lecture, then this IRQ channel is handled by the slave pig. And because of that, one has to make sure that not only the 12th IRQ is unmasked, but also the second IRQ channel has to be unmasked in order to allow for a cascade. So the cascade or the second IQ should be unmasked in order to allow for the slight pick to handle interrupts from the PS2 secondary port correctly. Okay, so that's a general overview of the PS2 interface. So now let's talk about how we can get information about what is happening on our PS2 keyboard. So, as I mentioned, the PS2 keyboard will usually fire IRQ number 1. This means that in your interrupt service routine 1, so the one that is mapped to the IRQ channel number 1, you should make sure that this IRQ channel is unmasked, by the way. You can write a simple handler. The way that information is obtained from the PS2 keyboard is extremely simple. So as I've said, the PS2 controller has a data and command port, and everything that you need in order to get the information from the PS2 keyboard is simply to read from the data port. So if you read a byte from I/O ports, hexadecimal 60, so PS2 data port upon IRQ1. So in your interrupt service routine 1, what you would have to simply do is read a byte from this PS2 data port. And what it will contain is something called a scan code. Now, this interrupt will be fired whenever a given key is pressed or whenever a given key is released. Now, the scan code will provide exact information on which key was pressed or released. So, generally, when you write a driver, you want it to be abstract. And that is because if you make it do a very specific thing, then it's not really good for the scalability of your operating system. What I mean by that is what your keyboard driver can do is simply store the scan code and perhaps interpret some information from it, some very basic information, but it shouldn't do a very specific thing with the scan code. However, you can then use your driver to generally play around with the information that the scan code gives you. It is very easy to search up PS2 keyboard scan code or something like that, and you will have a huge table, well, not so huge, of bytes and exactly what they correspond to, such as P key pressed or Q key released. You'll have a list of all of that. I trust that you're a competent programmer. You can implement this however you want. You can make a lookup table or something. You can map all the scan codes to ASCII characters and, for example, print them onto a VGA buffer. So yeah, you can do something like that, and just like that, you can actually interface with a keyboard. So the PS2 keyboard will fire RQ1, handle that interrupt, you read from the PS2 data port, which is hexadecimal 60, and this will contain the scan code, which you get to interpret however you want according to that table. You can just store it, and then you could, for example, convert it to an ASCII based on a lookup table that you want to print to a screen. It's as simple as that. And so on the topic of scalability, but this is precisely what I meant, right? So if your driver by itself was to print those characters to the VGA buffer, then that is limiting. Because let's say now you want to expand your operating system, and you don't just provide text input, but you, for example, want to make a video game. Well, the up arrow in a video game shouldn't, for example, go up. In terminal-wise, shouldn't like go a character up. What it should do is move a character, for example, forward or something, or upwards in a top-down video game. The idea is that the keyboard scan codes will have different uses, and you shouldn't be doing very specific things with the scan code in the driver itself. So drivers should be designed in a way that is abstract. So the PS2 keyboard is extremely simple. And that's already one input device, which I think is very cool. So the PS2 mouse is a bit more complicated, especially because of the fact that it has to go through an initialization procedure. So the PS2 controller starts in a state where only the primary port is considered to be active. So you have to initialize the second port correctly. So this is something that you can do at the start of your kernel, basically in whatever initializator thing that your kernel has, that your operating system has. You can do this before loading VIDT and such. You can just initialize the second PS2 port. So secondary port initialization. That's a weird R. So, how can you perform such an initialization? Well, first, to even say that you want to do anything with the second port, you have to send two commands. So, we know that the port, our PS2 command port is command. I'm going to write this up here actually, so that we can always refer to it. The command is hexadecimal 64 and data is hexadecimal 60. So first, what we have to do is send the following signals to the command. A8, that's a hexadecimal number. We're obviously sending bytes here. And then 20. Oh, also, in the handler for the keyboard, remember to send an acknowledgement. So I already talked about this, but always remember to send the command 20, which is acknowledgement, to the master and slave pick, so 20 and AO. I always remember to send acknowledgements to say that, hey, you're done with handling the interrupt once you've gotten the scan code from the PS2 data port. Back to this. You have to send these two to the commands to even inform that you want to do anything with the secondary PS2 ports. And once you're done with that, what we want to do is enable the secondary PS2 port. And in order to do that, we have to set a bit to 1. In fact, it's the second youngest bit of something called the status. And the status is simply, once you've done this, the data port will contain something called the status. What you have to do is you have to retrieve that status and make sure to set this second youngest bit to 1 without changing anything else. Then we will do a command of, hey, I want to send a status to modify. Then we will send this modified status to the data port. And this is how we can enable the secondary port. So we've sent this to the command port in order to say that we want to do something with the secondary PS2 port and that we want to obtain the status. And now we're going to read the status from data. By data, obviously I'm referring to the data port, OR it with 2. Obviously, if you perform an OR operation with 2 in binary is obviously 1, 0. So, well, then you have a bunch of zeros afterwards. So if you OR it, it means that no matter what, you will keep the entire state, but the second youngest bit will be a 1. And then we have to send the command that we want to modify the status and send this modified status to the data port. So we have to send hexadecimal 60 to command, and then send modified status to data. So you can save this in a variable, you can OR it with 2, then you send to the command port, so 64, you have to send the byte 60, and then you can send the modified status to data. So what we've done here is we've managed to enable the secondary port, but that by itself doesn't give us much, because cool, now we consider it enabled, the PS2 controller knows that this can be used and it will fire its interrupt, but it won't actually give us any useful information. So we have specified that we want to do something with secondary port. We've gotten the status and we've modified it. We've sent the command to modify it, and we've modified this bit such that it's now enabled. And now we have to also do something which is called setting the secondary port to streaming mode. So basically, we'll require for this secondary port to report information, to report data in something called streaming mode. And the way that we can do this is first we have to send a command of, hey, I want to modify something about the mode of this port. And this command is d4. So we send the d4 command to say, hey, I want to modify something about the secondary port, and then we want it we want to set it to streaming reporting information mode. And the specific mode that we want to set it to, the sort of thing we want to change about it, will be specified by sending a corresponding code to the data port. So the mode that we want, so information reporting enabled, that is F4. So we have to send F4 to the data ports. Okay, and once we've done this, we should have not only our ports enabled, but also information reporting enabled, which means that not only will this port fire interrupts when the mouse is moved, but also we will get information reports about what the mouse has actually done that we can use in order to write a proper driver. It is also good to check if all of this has been done correctly, and this can be done by checking the data port. And if the data port is FA, then this means if the data port, if the contents of the data, I don't really like this notation. If data contains FA, because it's not equality, because since by data port I'm referring to this, I don't want to say that it equals FA. I just want to say that if the data port, if we read from it, and what we read is FA, then this is an acknowledgement. So this means, hey, you've managed to configure everything safely. So again, in order to properly initialize the PS2 secondary port for our purposes, we first send a command that we want to do something with the secondary PS2 port, and then we want to get the status. We read the status from the data port, and we change one bit, which will be necessary for enabling the port. Then we send a command to send a modified version of the status. We send the modified status, so order with 2, so now we have this bit enabled, and now, after we've done this, we have enabled the secondary PS2 port, but it doesn't report any information. So we say that we want to change something about the way that it sends information, just anything about the port, which is D4, and we send F4, which means streaming report information mode. And once we've done this, we can also check if the data port now, if we read it, it does contain FA. If yes, that's an acknowledgement that we've done everything correctly. Be sure to obviously replace every command data with those ports, which should be the same for every PS2 controller according to a standard. Okay, so this is the whole PS2 secondary port initialization procedure. So now I'll be working under the assumption that what is plugged into the PS2 secondary port, and this is a pretty safe assumption, is a mouse. So whenever the mouse is moved, not one, but actually 3 interrupts will be fired through the same IRQ channel, which is 12. So there are different timings and such. We don't actually have to care about the timings themselves, but we will have to store the 3 pieces of information that it gives us into some buffer that we can actually deal with. So fundamentally, the goal of our PS2 mouse driver will be to obtain a buffer which contains different information about the mouse. We can also sort of process that information to, for example, output the change in X or Y position, whether something was clicked, just as a bunch of variables. How you design your driver is up to you. What matters is that the driver is relatively abstract, and then based on the driver, you can make some concrete implementations, such as right now, if you only have a VGA buffer available, you can make a little blinking cursor as like it can simply be a character that is fully white, right? And it moves according to the information given through the PS2 mouse. I will just be talking about how to actually get that information based on the data reporting streaming mode, but I've just specified how to properly initialize. So the PS2 mouse, whenever it is moved, it will actually send 3 bytes. But it will only send 1 byte for every interrupt. So you have to make a buffer. This buffer will be 3 bytes, and you can use a modulo operation, modulo 3, right? So that it goes back and just says the 0th position first and second, 0, 1, 2, 0, 1, 2, and so on, for every collection of such 3 packets that the PS2 mouse sends. So the first byte that will always be sent, or byte 0. Oh, by the way, you read those bytes that it sends every time from the data port. So you read a byte from data upon IRQ12. Make sure to unmask the cascade as well, and also unmask IRQ12, obviously. And in your handler, so in your interrupt service routine 12, what you should do is you should read a byte from the data port and the PS2 data port, of course, which is 60 in hexadecimal. And you should store it in a buffer, right, which the index of a buffer should start at 0 and then you can increase it modulo 3. So that you can get those whole buffers that the mouse will send. So it should fire 3 times, and the first byte that it sends, or the 0th byte. So the oldest bit will contain the Y overflow. This means that if the if your mouse was moved vertically to an extent that none of the values specified fully store it, so the values will be at the maximum, but the mouse has moved even more, then this bit will be, or the Y overflow bit will be set to 1. So this will happen if you move your mouse like this, or if you move your mouse like this. And this will result in this bit being 1. Then the next bit is going to be your X overflow. I'm obviously starting from the oldest bit here. Oh, well, not so obviously, which is why I'm going to specify it. So this is your X overflow. So if you move your mouse like this, or if you move your mouse like this, then this bit will be set to 1. Then, in the mode that we have right now, we don't really have to care about this, but the next 2 bits are the Y sign or X sign. So, in the mode that we're currently in, and that our PS2 mouse is in, we will have the entire information about precisely, including the sign, stored in 2's complement in the byte that will contain our X and Y offset. Not offset, delta. So what was the change? So we don't actually need these, but if you'll need like more precision, well, not more precision, but if you want to analyze if someone has moved the mouse even more, you want to store more of those positions, you can store very dynamic mouse movements, so you'll need this extra bit. If you'll need this extra bit, then the sign bit will be stored in this first byte that will be sent. Then the next bit is going to be 1. And then you have 3 bits, which all correspond to whether an input was given in one of the mouse buttons. So this is the BM or button middle, right? So if the middle mouse button was pressed, then this over here will be set to 1. BR, so the right mouse button. If the right mouse button was pressed, then this bit will be set to 1, and BL, so if the left mouse button was pressed, then this bit will be set to 1. So all the information about the mouse buttons will be given in the 0 byte. Yeah, okay. So the next byte that it will send, which should be in your first position of the buffer, is simply a whole byte in stored in 2's complement. So a standard signed 8-bit value signed char. Or car, however you want to pronounce it. And this is going to be your delta X. So what was the change in X? And this can be either a positive or a negative number. And if you're moving your mouse to the right, then it will be a positive number. If you're moving your mouse to the left, it is going to be a negative number. So there's this whole byte, and then the last byte that your PS2 mouse will send is delta Y, which is going to be how much your mouse has moved vertically. However, so this horizontally, this is vertically. However, an important note is that some people have different, depending on different systems that they use, computers that they've used, they might have a different intuition for what happens when you move your mouse up. So I've met some people, and this is more rare and rare nowadays because this isn't the default, and on most operating systems, most computers, this isn't really the default. So this is a bit more rare now, but I still met some people that consider it intuitive when they move their mouse up, their cursor moves down, and when they move their mouse down, then their cursor should move up. And this used to be fairly common, and it's not as common nowadays. Most people nowadays consider it intuitive for the mouse cursor to go up when they move their mouse up, and for it to go down when they move their mouse down. And if you also find that intuitive, then you'll have to actually reverse this, because this delta y is given like in the first example that I specified. So if you want your position to be positive if the mouse is moved up, when obviously by up I mean like when you look at it top down, then you'll actually have to reverse it. So I'll just say that this should be possibly negated, or more like potentially to negate. So this is something that you'll have to potentially negate. And you will have to negate it if you want it to be intuitive in the sense that I just specified. Okay, yeah, and that is pretty much the 3 bytes that it will send. If you can also initialize the PS2 mouse a number of ways, and you can, for example, initialize it to, as I said, for this to not be 7 bits and 1 sign bit. You can make these 8 bits and then use the Y sign and X sign bits from this byte. And you can also set it to 5-byte reporting mode, so it will actually send byte 3 and byte 4, and those are used for some extra configuration, and also the middle, the middle, the scroll, right? So the middle scroll, and it'll also have information about how much it was scrolled. I don't actually fully know the formal nomenclature of this, but you probably get the idea. Okay, yeah, so you can simply store this in like X offset and Y offset, or delta X, delta Y, whatever you name it. You can store absolute positions, but it will be modified by this, so you'll add this. If it's negative, then it will obviously subtract it. You can use these to detect which mouse button was pressed. You probably don't care about these too much, so you'll probably just use these, and you can use these, and again, you should just make your driver abstract, and then you can use this information however you want. But that's how you obtain it. You read this data byte upon RQ12 firing, and the RQ12 will fire with the initialization that I provided 3 times, and will provide bytes just like that. And the data port is hexadecimal 6. Oh, of course. And don't forget, after you're done with handling all of this, send an acknowledgement to the master and the slave pick that you've finished handling the interrupt. Which is command 2.0. And you have to send it to ports 2.0 and A.0, which correspond to master and slave programmable interrupt controllers. Okay, so congratulations. If you managed to implement this, then you have keyboard and mouse support in your operating system. So you can generally now play around with this, use this information in order to modify the VGA buffer in whatever ways you want, and you can make a simple piece of software, I guess that's one way you can call it, where a piece of code where it uses the mouse position in order to move a little white character, just white character, and once you click, so it detects that that bit is 1 based on the buffer that you read. It detects that, for example, the left mouse button was pressed, and it changes the position where it should write characters, and whenever you press a key on your keyboard, it fires RQ1, right? You read the scan code, you send an acknowledgement, but then you take the scan code, you can use the lookup table or something, convert it to an ASCII, and display the ASCII character. You can mess around with displaying, obviously, what ASCII character is printed may also depend on whether the shift key is pressed or whether caps lock is pressed. So those are all mechanisms which should be relatively easy to implement, and they're not that related to operating system development. They're just simple programmer tasks related to logic. So you can just generally have fun with this information, and congratulations, that's a keyboard and mouse for use. So now the user has some way to interact with your operating system. Not really a way to interact with your operating system directly, but at least the user can do something with your software that you run on that computer directly on the CPU, which I think is cool. Okay. So that's the PS2 interface. I'd also like to cover something called the Peripheral Component Interconnect. So the Peripheral Component Interconnect, or PCI, is a bus that probably most viewers have heard of and have used. It is a very common bus which is used for connecting peripheral devices. Well, the original PCI is a bit outdated. And currently there's a slightly newer bus called PCIe. But I will talk about that in a second. For now, there's obviously, right, we don't communicate directly with the bus. There's no such way to do this. However, the bus is controlled by, the PCI bus is controlled through a PCI controller. So the PCI controller, it controls 8 PCI buses. 8 times you have a PCI bus. So yes, so when people say PCI, they usually think of one bus. However, in reality, the PCI bus is physically constructed out of 8 physical buses. If we're talking about the legacy, the classical PCI, those are parallel buses. So Peripheral Component Interconnect is an interface that was created in order to generalize and abstract away peripheral connections. So there were supposed to be 8 buses, and to each of them you could just connect the abstract notion of a device. So each bus can handle 32 devices. Now, this doesn't have to be device in the sense of a mouse, a keyboard, a speaker. This can also just be an extension card or anything that does some computations, or just anything that has to interface with any sort of way with the user of a computer. So 8 times 32, so that means that you can actually have, if I'm not wrong, I'm not mistaken, 256 devices, and each device, I'm going to check this. This is 2 to the 5th, this is 2 to the 3rd, so it's 2 to the 8th. Yeah, that checks out. So 256 devices in total that can be controlled through the parallel PCI buses. And each device actually can have 8 functions. So this is a pretty wise system. They decided that, okay, PS2 is pretty good, but you can sort of see that it's made for those 2 very common devices, a keyboard and a mouse. And it's a pretty safe assumption that any computer user is pretty much going to use a keyboard and a mouse. They're nowadays very, very common peripheral devices. But what about other devices? They don't have such standards, and you shouldn't just make all those different ports for a printer and this thing and this thing, and see they can follow different standards, and they should follow different standards. I mean, there should be a general standardization, but they shouldn't all be exactly the same, right? And this is why creating a general abstract interface, which could allow for the operating system to in a general way interact with peripheral devices and extension cards, this was a pretty wise idea. So as an example, you could have a sound card, right? And let's say that the PCI controller would control those buses, and the sound card, for example, be on the PCI bus number 3. And it could be, for example, device number 7, and it could, for example, have a function 0, which would be sound output, and, for example, function 4, which would be sound processing, right? And you can reference all of that and then in a simple way and interface with this device through this parallel bus. There is, as I mentioned, there is a newer version of PCI. It's something called the PCI-E bus, or Peripheral Component Interconnect Express. So if anyone watching this is a bit more interested in hardware, they probably know that PCIe greatly differs if it comes to a hardware perspective. And that is because the PCIe buses, because it's still physically constructed out of 8 buses, they're all serial, not parallel. And that is because back in the day, you actually used to have a lot of parallel buses because people used to think they're faster. Because, well, it does seem pretty logical that whenever you would have data sent at the same time, it would be faster than sending data bit by bit. However, in reality, it turned out that parallel buses, they can have more conflicts, they have a larger electromagnetic field, which causes for interference, and there's a lot, and I mean a lot of error correction. And not only that, whenever you need to correct an error, you have to send all the bits again, which even increases the potential chance of another error. So a lot of error correction caused that even if in theory parallel buses should be faster on average, serial buses are actually way faster because they require for less error correction, and whenever there is an error to correct, only one bit has to be resent. And this is why many buses were had newer versions which were serial and not parallel. And one example is the PCI bus, which was replaced pretty much entirely by the PCIe bus. So huge hardware difference, and also not only it didn't just replace the PCI, it replaced many parallel interfaces. For example, there used to be another parallel bus called the AGP, or the Accelerated Graphics Port. Many of the viewers will probably also remember that back in the day, you had a graphics card or a video card, and you would have to place it into the AGP parallel bus. But that's not something you do nowadays. PCIe comes in different slot sizes, and it's managed to replace PCI with, for example, the slot 1 size, but with bigger slot sizes, it also managed to, for example, replace the AGP parallel bus, and therefore modern graphics card work through a synchronous serial interface, which is a PCIe. So usually nowadays, when you have a graphics card and you put it into your computer, you put it into your PCIe slot. So huge hardware difference. However, those are actually very similar from a software perspective. So one key thing that should be mentioned is if it comes to actual communication, software communication, you can, so PCIe from software perspective is actually backwards compatible with PCI. And because of that, I'll be presenting a way to communicate with a PCI controller using the I/O bus of the CPU. And all of that will also work for PCIe, and it's going to be perfectly fine, because PCIe is also made backwards compatible, so that it can the PCIe controller can also be communicated through the I/O bus in the exact same way as a PCI controller. So it's going to work perfectly fine. This is theoretically not the proper way to communicate with PCIe. And that is because there is another interface called the ACPI, or the Advanced Configuration Power Interface. I'll probably also be talking about it in a future lecture. And you can obtain the base address of a memory buffer from the ACPI. So a memory address where a buffer begins of the PCIe. So you should actually communicate with the PCIe for a buffer in memory and not for the I/O bus. And you can get the base address of this buffer, so where does it begin, from a table that you obtained from the advanced configuration power interface. So even though you do that, the format in which information is sent and received is precisely the same. So again, PCIe and PCI, completely different from a hardware perspective, very similar from a software perspective, and even backwards compatible. Okay. So now we can sort of understand the goal of PCI. You know, it was supposed to be a bus to generally communicate with peripheral devices, to enumerate peripheral devices, and to communicate with them, as well as with extension cards. We're split into 8 buses. Each bus can have 32 of those devices, which can have 8 functions. There's a newer interface called PCIe, very different hardware-wise, very similar software-wise, is backwards compatible, so we can simply use the I/O bus. That's what we're using PCI, and it will work for PCIe as well. Great. So the PCI controller obviously has a command and data port, as any other controller. And in hexadecimal, the PCI command port is CF8. So that's the PCI command port. And CFC is the PCI data port. So in order to write or read information, we should generally make functions when actually implementing this in code that are used for writing and reading to the PCI bus. But we have to specify exactly to which function of which device of which bus do we want to write or read. And in fact, for every function of a device in a bus, you also have a lot of information. A bunch of different information. You might need some of it, you might not need some other things. That is why you also should include another parameter, which is something called a register offset, which is basically what information will you want to receive. I should also mention that all the I/O bus communications this time, they will not be 8-bit, because all of the I/O bus communications that I previously talked about were 8-bit. We are receiving and sending individual bytes. Over here, we'll use the wrappers that I talked about, out L and in L, so out long and in long, which means that we'll be sending and receiving 32-bit values. So in order to so let's start with reading some information. So let's say we want to obtain some information. Whenever we have specified a bus, a device, a function, and a register offset. And so to the command port, we'll have to send something called a PCI ID, which will unambiguously specify all of that information. So a PCI ID is a 32-bit value, which is why we'll have to use a 32-bit I/O bus communication wrapper. And the PCI ID always starts with a 1. So it starts with a 1, and you can generally implement generating this ID based off of the parameters provided, just using bit shifting and ORs. It really shouldn't be that difficult. So you have a 1, then you have a bunch of zeros, and until you go to position 18. By 18, I mean that you consider this position for 31. So you consider the oldest bit 31, the youngest bit 0, and using that nomenclature, whenever we have bit 18, this is where, from 18 to 16, this is where your bus ID should go. So we have 8 buses, right? So this means that you have values from 0 to 7, and this means that 3 bits are enough. So you simply use these 3 bits in order to specify the information about the bus that this device is found in. And then you have to specify the device number itself. So you have your device will not fit the E because this is a 5-bit value. So it goes from bit 15 to 11. So as I said, there are 32 devices. So from 0 to 31, again, 5 bits are enough to store this. And then you have to specify function. Again, 8 functions per device, which means that 3 bits are enough. That's bits from 10 to 8. And then we have bits from 7 to 0, which means we have a byte remaining. And this byte should contain our register offset. However, since these are 32-bit values and such, and it is generally everything is designed in a way not to waste space, the register offsets are actually sort of grouped into bits. If you consider every piece of information to be a register, right, then it sends 4 of them at a time, each one being a byte, which means that it actually groups those register offsets into sort of groups of 4, which means that this register offset that he wants to obtain will actually have to be ANDed. I cannot draw an ampersand with FC. Well, that's just a hexadecimal representation. But the idea is that F is 1111, C is 1100. So this will make it such that the last 2 bits are not significant, that they will not appear, they will be certainly 0. And that is because with 2 bits you can represent 4 combinations, so only the rest will matter, which means that it will group those into those groups of 4 that the PCI was designed to intake. So you should end this with FC in order to ignore the last 2 bits, because the PCI has sort of grouped this information of the different registers into 4, so register offset should be, this register offset should be a multiple. Okay. Great. So now, once we send our PCID, so this entire PCID has to be sent to the command port. And once we've done this, we can read from the data port. So then read from data into something that I will just call TMP for temporary. And in order to, from this TMP, actually obtain the information that we want, so the information at a given register offset, about a given function, about a given device, of a given bus, what we will have to do is, so this is right where our register offset actually comes into play, because if we specified register offset 0 and register offset 2, you'll see that once we ended with FC, we will obtain the same thing, but we want to get something else because we want to get something from a different register offset. And that is because what we actually have to return from this function is TMP shifted to the right by our register offset modulo 4, because as I've said, we sort of want this to, we have grouped this into groups of 4, right? So we only specify the register offset after what we haven't specified. So it's modulo 4, and it's shifted by 3. So you shift this to the right and this will give you the proper value that you want. Because, as I said, they're grouped into those packs of 4, so we get those 4 registers, and to get the exact register, you just shift it to the value that you want according to this value modulo 4, so we only want this. Which offset do we want from the specific group of 4, and is shifted by 3 to the left, because that's just the format that the PCI gives it, and so we have to shift this so that this shifting is correct. That's just the format that PCI gives this information back in. So once we return this, we have read an information from a given offset of a function of a device of the bus using our PCI ID. And obviously the data port that you're supposed to read from, that's a 32-bit value that you should read, by the way. You should read the TMP of anything. It should be an unsigned int or something. And the PCI data port is hexadecimal, it's the MC. Okay, so that's reading, and a writing function would be precisely the same, except that you specify this PCI ID in the exact same way. You can show it the same way. You send it to the command, but instead of reading from data, you send something to data. So just simply send the information, which is given as a parameter in the function. Let's say you write PCI bus. Okay, so now we can read and write using the PCI bus. That's great. Now, using those functions, we can actually enumerate PCI devices. We can enumerate PCI devices, which means that we can display all the PCI devices which are currently plugged in and give some information about them. So that's a pretty common use case of a PCI bus. So the enumeration process is relatively simple. It is going to be constructed out of iterative loops. And we'll be simply iterating through 8 buses. We'll have a loop inside this bus loop that'll iterate through all the devices. And in all the devices, we have to iterate through all the different functions. But that is a lot of operations, and the actual amount of the devices that will be plugged in will be way smaller. But this is just something that you have to do because you have no way to obtain the information of, hey, there's a device at this exact PCI ID, or there's a device on this bus in with this device number, and it has these and these functions. You sort of have to do it through detecting everything yourself and checking the information that are provided. So, there are different, you can probably make something like a struct. You can make a structure which can be called a device descriptor. And this struct can simply contain different information that might be useful about a device. So this can be, for example, the vendor ID. Based on the vendor ID, you can check what sort of manufacturer made this device. Then you can get the exact device ID. You can search up exactly what this device is. You can also have the class, the subclass. I'll show an example, a use case of this later. You can get the interface that it's supposed to use. You can get its revision. You can even get interrupt. Yeah, so you can get a bunch of useful information. The PCI also allows you to get something called bars, or base address registers. So those are registers that store base addresses of buffers if your device or extension card uses such a memory buffer. Right? So many devices and many extension cards, they're supposed to be communicated through the RAM. So you have a memory buffer, you write and read information from that memory buffer in order to communicate with that. And in order to do that, you have to know where that buffer is in the memory. And the PCI usually allows you to check this for a given device using something called base address registers, which are also relatively easy to obtain in a similar manner. But I decided that they're not that important for our purposes, so I'll just be talking about how to get these. So once you've made such a struct, you can make a function such as a get device descriptor, right? And it can take a bus and a device as well as a function, just as parameters. And then it should read from the PCI bus into 32-bit values from the following register offsets. So the vendor is going to be an offset, and it's also common to write this in hexadecimal. 00 is 02. Class is at 0B. Subclass is at 0A. The interface is at 09. Revision is at 08. And then the interrupt is at 3C. So you simply have to perform the read PCI instruction in order to get a 32-bit value with the bus function and device specified as a parameter to a function like get device descriptor or something. You can store all of this in a struct. And you can simply read from these offset registers. Okay, so now you have different information about all of the devices. So as I said, we have 3 iterative loops, and we have obviously the main sort of body, our main code in the last loop, which is going to iterate through the 8 functions. Though before you do that, in the previous one where you have devices, you can actually check whether this device is has multiple functions. So this can be useful, this can speed up the enumeration, because if you know that a device only has one function, then you don't have to iterate for all of the functions. So in order to check whether something is multifunction, and this is, you can place it in the loop which only has the device, because you always check it for the 0 function, so it doesn't have to be in the function loop, which is very convenient. So in order to check whether a device is multifunc, whether it has multiple functions, you simply have to read from, you have to read you read PCI using the current bus, the current device. The function should be 0, and the register offset should be 0E in hexadecimal. And if this is precisely one shifted by 7, so it's 1 followed by 7 zeros, so you can just AND it, right? You can return read PCI and everything, AND it with this, and if this expression is going to be true, right, you can return this expression. If it's true, then it is multifunc, and if it's anything different, so if it's false, then you know that it only has one function or 0 functions, so the device doesn't even exist. Okay, and now how can we check if a given device even exists? Well, you can usually check this off of vendor ID, because the vendor ID is standardized to never be 0 or the maximum, which is FFFF. So you always have to check in this loop of functions. You have to check is the vendor ID either 0 or FFFF in hexadecimal. And if it is, that means that this device does not exist. And it means that you can go to the next device. And it keeps on doing that for over 32 devices. If the vendor ID is anything else, then you can display all the different information because they're valid pieces of information about a proper device. If you have checked that a device exists, but it's not multifunc, that means that you can just do one iteration for one function and you're done. If it does have multiple functions, but you don't know where they are, so you can't just terminate the loop once you encounter vendor 0 or vendor max. But if you encounter vendor 0 or vendor max, you can continue to the next iteration of the loop. So you don't have to do all of this, but you can't terminate it because, for example, you can have the first function of some device at function 0, and then the next one could be function 3 or 4. So you can have space in between those, and all those functions, they will return vendor 0 or FFFF. But that doesn't mean that there aren't any functions later. Okay, yeah. So you can simply iterate through all of that. So all of the buses, all the devices, all the functions. You can check whether the vendor ID is valid, so it's different from 0 or FFFF. If yes, you can get the full device descriptor and you can properly display it on the screen, and that's how, or you can get it into the debug log. That's probably a better idea for now. And you can debug log into the COM1 port, for example, all the different informations about all the different devices that are plugged through the PCI port, and then you can check what is the device, what vendor does it come from, and so on. So that's one very common use case of the PCI. Very nice always to see in a debug log or something like that, which is enumerating PCI devices. So enumerating the devices that are connected. And I can show a use case of how those values can be used. So, for example, the class and subclass. There are standards that specify, for example, oh, if the class is this and the subclass is this, then you know that this device is something. That is very abstract, but I will provide a very concrete example. According to the USB-IF standard, if the class is 0C, and the subclass is, I'll write a better 0, is 03, then this means that what you've got yourself here is a USB device, such as the USB controller. So this can be a USB bus controller or a host controller interface, right? So if you find, you can, for example, enumerate all the devices, and whenever you find a valid device, you can check whether the class is this and whether the subclass is this. And if both conditions are satisfied, then you got yourself a USB device, which I think is pretty cool to detect. So you enumerate the devices, they all are printed in the debug log, and for example, you can make a little thing that pops up under a USB device that just says USB device, and there's a little upward pointing. Yes, so that is pretty much how to use the PCI, how to write and read, and how to get a device descriptor. I recommend also looking a bit more into base address registers because those might be useful. And this was the general idea of different peripheral interfaces, how you can use peripheral interfaces, what peripheral interfaces are used. And I provided some information on how to use the mouse and keyboard. So the primary input devices that are used on computers. So that is pretty much everything that I wanted to talk about in this video. In the next video, I'll probably talk about graphical output, which in my opinion isn't something that you should focus on that much, but the reason I want to do it now is I want to sort of check this box where I said that ROS should be able to manage I/O devices. And since I talked about input devices and the common peripheral interface, and if I talk about an output device which is graphical output, so interfacing with a video card and some display. I think that it's pretty satisfactory for that condition which I specified. So thank you very much for watching this lecture, and I hope that you'll watch other lectures of mine.